Welcome back to ECE 340. 1 month left, essentially. And in that time frame, you have 3 more homework assignments, actually 4 more homework assignments. Homework number 7 is due Thursday. Then we get homework 8, which will be dealing with Fourier series, and that's chapter 6 material. If you want to start reading up on that, that's encouraged. Exam number 3 is a week from Thursday. That will be our last midterm prior to the final exam, and you'll have to look at the syllabus. I'll try to remind myself when the final exam is, but I think it's on a Wednesday during finals week. It's not on a Tuesday, so plan accordingly, and I'm not sure when it starts, whether it starts before this class normally begins or after. So I'll try to get that information, but be thinking about your schedule and making sure that you're okay for a Wednesday final. I believe it's not a Tuesday, Thursday final in this class, even though this class is a Tuesday, Thursday class, and you might check your other classes to make sure you're not getting caught off guard in that way also. What I want to do today is really pick up with where we left off, which is filter intuition. I know I'm going to run out of time starting there, so what I want to do is just give you some background information about filters. You should know this. This is 320 material, and I'll just point you back to 320 sections in a book that talk about passive filters and active filters in terms of how do you build these devices that we're designing now. We will then talk about how do we pick the order. And this is maybe not, oh, let's just plug in a formula. Let's actually start thinking about if somebody gives us a word description of this filter or this system's behavior, can we pull out or extract the necessary information to guide us in how big in terms of order we want that filter to be. What's little n? Then we'll talk about the 4 different types of filters that we will focus on here, which are low pass, that's what we've been focusing on mainly, high pass, band pass, and band reject or notch filters. And what is the relationship between the poles and the zeros? Are these transfer functions strictly proper? Are they proper? Can we make sense of that type of information relative to what kind of shape this frequency response will be for this given pole zero pattern? And we'll talk maybe even about designing a band pass filter and how we might do that. Then hopefully we will have time to talk about sinusoidal steady state. You should know this. We've already hit it many, many times, but this is getting us ready for the next stuff, which is chapter 6, Fourier series. Fourier series gives us another tool to carry along so that we can now analyze signals and systems. Right now, today, we're talking about the system idea. How do we build a filter? How do we create this system that shapes the frequency response of a given signal or signals? Once we have that, we may say, oh, here's a periodic waveform that's being applied to this system, which today we're talking about those systems being filters. But it might just be a channel that your communication is going through. That might be the filter, and you now want to know what's that filter doing to my signal as that signal is propagating through space or through some other media. Let's now talk very quickly about filter realizations, and I've tried to give you a chart. Maybe it's a little bit busy, but the black numbers, those that are not enclosed in parentheses are the figure values, and those in parentheses are the page of Nielsen and Rydell's 9th edition of electric circuits relative to these different types of filters. passive filters, which are just RLC filters. You don't require another energy source or a power source to make those work. And then active filters, which provides us a little bit easier method for building up higher order systems. And these active filters now are just op-amp based filters. There's different ways of realizing all of these. You could do a low pass filter 4 different ways, depending on how you want to build it up, whether you want it to be passive with an inductor and a resistor, or with a capacitor and a resistor, or if you want to use an op-amp configuration. Similarly, you could build high-pass filters, or you might want to just pass a certain frequency band, a band pass filter. Or you might want to notch out or reject certain frequencies. This just provides you with a reference to go back and say, oh, I need to build this. How do I do it? Well, this will now get you thinking about the different kinds. And if I said, oh, sketch me a low-pass filter, hopefully you're all thinking about this RC that we've done in the past. You have a resistor and then a capacitor, and we're measuring the voltage across that capacitor, and the input is the voltage impressed across that series combination of resistor and capacitor. If you wanted a high pass, now you just flip the 2 elements with each other and you have a CR, and now you have a high pass type filter. And you can do other manipulations. Now if you're doing band pass or band reject passively, you need a couple of energy storage devices. You need a couple of poles. And that's then included in that particular information. That's all I really want to say about filters and where you can go to reference that material. And there's a little discussion in the book about second order filter parts. And you'll need to, if you're building up filters, you'll probably want to factor your denominator into real and complex factors and realize a second order and a first order combination and put those together. Question? So if I scroll to the right a bit, hopefully, wow, if you were that quick to get all of that, I'm impressed. Those are then the page numbers associated with, and if you don't write that down quick enough, this will be posted on D2L and you can copy that down at a leisurely pace, more leisure maybe. Yes? I was just thinking about that. I believe those are maybe the more popular techniques to use relative to those 3 or 2 different configurations of the RLC. This is probably a more utilized design. That's what the star is there for. That, I think, then covers the notation of that particular table. It's a little bit busy, but hopefully it's clear what I'm trying to communicate with that table. Let's now talk about low-pass filter characteristics. And all of this, if you think about the low-pass filter, if I simply said, here's omega, and here is the linear magnitude h, then if I said, oh, what's a first order filter response look like? That now might start out and then it sort of rolls off. Now I say increase the filter order, but maybe preserve the same 3 dB point. Now you might have something like that in terms of a curve, so that these curves are illustrating what happens when you increase n, little n, which I'm defining to be the filter order. Relative to these shapes or behaviors, you can identify 3 different regions relative to the frequency axis omega. You could say, oh, this particular region right here is what I want to pass, and this is now called the pass band. Over here, you might say, these are the frequencies that I really don't want to have, or I'd really like to kind of stop or attenuate those. This is now typically called the stop band. And the interval between is where it's transitioning between the pass band and the stop band, and that's now called the transition band. Some of the characteristics that occur as a result of increasing the filter order. One is, if you're dealing with a Butterworth,